Hi all. In the last class, we have discussed the properties of power series, and we have discussed theorem 8.1. It deals with some consequences of the power series defined as a function and its corresponding derivatives. And we have seen that in terms of the derivatives of function, we can get the values of the coefficients of the power series. In this session, we have discussed the power series with the radius of convergence is equal to r. So here we consider those power series in an open interval, and here in theorem 8.2 we will discuss power series with defined on -1 open interval -1 and we can extend that power series to the endpoint to one endpoint, that is x equal to 1, if the power series converges at that point. So that is theorem 8.2. To define, this is the statement of theorem 8.2. Suppose sigma Cn converges, that is sigma n equal to 0 to infinity. This infinite series, this is convergent, that is our assumption. Put f of x equal to summation n equal to 0 to infinity Cn x raised to n in this interval. This is an open interval -1 to 1. Then since this is convergent, this is obtained by putting x equal to 1 in this. Okay, so even though this function, this power series is not defined at that point, this power series is not defined at x equal to 1. Even though it is not defined at x equal to 1, we observe that when you put this x equal to 1, then this is convergent. Okay, if this is convergent, then you can easily get the limit extends to 1 f of x equal to summation n equal to 0 to infinity Cn. Okay, in case this power series converges for x equal to -1, you can get the same limit extends to -1. F of x will be that series obtained by putting x equal to that value. Okay, so this is the theorem 8.2. So first of all, we set to prove this, we set Sn is equal to, we write the value of Sn is equal this is small sn, so we write Sn as the partial sum of the series. Sn is equal to the sum of the series and summation n equal to 0 to infinity Cn, that is C0 plus C1 plus etc. Cn up to Cn. And for the convenience, we write we define, or we put a symbol s -1, this is equal to 0. Okay, so this is just a symbol for the convenience. Then we have summation n equal to, we write in this case summation n equal to 0 to m Cn x raised to n. Okay, so this is in fact this is equal to in terms of, we can write Cn is equal to Sn minus Sn minus 1. From this you can write Cn is equal to Sn minus Sn minus 1. Okay, from this definition you can write like this. Then substitute for that value here, summation n equal to 0 to m. The Cn can be written as Sn minus Sn minus 1. Okay, so into x raised to n. So this is the substitution. Then we rearrange this summation as this is equal to summation n equal to 0 to m. We open this bracket, Sn times x raised to n minus summation n equal to 0 to m Sn minus 1 times x raised to n. We have already denoted or defined this as m minus s minus 1, that is equal to 0 here, and we rearrange this as summation by taking one term from this. You can write this is Sm times x raised to m. We extracted the last term of the first sum, so the remaining will be sum starts from n equal to 0 to m minus 1 Sn x raised to n. So this is the splitting of the first term, and second term we write this is summation n equal to we substitute this n minus the second sum, we substitute n minus 1 is equal to some k, n minus 1 is equal to k, so we have this n is equal to k plus 1. Now whenever n is equal to 0 we can get k is equal to minus 1. Whenever n is equal to m we have k is equal to m minus 1. Okay, so this is the by putting n is equal to m in this equation, you can get k is equal to m minus 1. Okay, so if we replace the summation in terms of k, we can get this k starts from minus 1 because n starts from 0 here, and all the way up to this m minus 1. Okay, so this is the limit, and this sum will be this s n minus 1. Instead of n minus 1 we put k here, and if n is equal to k, since n is equal to k plus 1, we have x raised to k plus 1. Okay, so this is the new sum. This is exactly the same sum but in terms of k. Now we write this is equal to sm x raised to m plus we write this as summation n is equal to 0 to m minus 1, this s n x raised to n minus summation k equal to 0 to m minus 1. Okay, we change if we consider the first term, the term corresponding to k equal to minus 1, the coefficient will be s minus 1. S minus 1 equal to 0, so we can remove the first term from this sum. So we start with again k is equal to 0, sk x raised to k plus 1. Okay, now we can take this 1x from this. This sum starts from the term s0. S0 is defined as c0 itself. So s0 x raised to 1, x1 s1 plus x raised to 2 plus etc. So this all the terms of the sum contains x, so we can take 1x from the sum. Then that will be sm x raised to n, this is the first term, and summation n equal to 0 to m minus 1 sn x raised to n. And if we take 1x from the sum, the second sum, we can get x times k equal to 0 to m minus 1 sk x raised to k. Okay, now these two summation can be grouped. Okay, this is from n equal to 0 to m minus 1, and this is equal to this summation from k equal to 0 to m minus 1, and this you can replace this k with n. Then you will get sm x raised to m is the first term, and the second sum will be n equal to 0 to m minus 1 sn x raised to n minus x times. If you again replace this k by m, then k by n, then this starts from n equal to 0 to m minus 1 sn x raised to n. Okay, so you can simply resubstitute k is equal to n, so that will be n equal to 0 to m minus 1 sn x raised to n, which is equal to then this the left side will be n equal to 0 to m c n x raised to n. Then this sum, this will be the summation. We can combine these two sums again, so this is summation n equal to 0 to m minus 1. When you combine this, you can take 1 from this summation sn x raised to n out from these two terms, then the remaining will be 1 minus x. Okay, plus I will write the first term sm x raised to m. Okay, so what is the idea of the idea here? When you take m tends to infinity on both sides, this term tends to 0, because this x is always less than 1. So as m tends to infinity, this x raised to m tends to 0, and this term tends to 0. And again this again as sm, when you consider these two terms, we can say that this converges to some s, and sm tends to infinity, because this is the sequence of partial sum of the convergent series. Okay, series Cn. and this x raised to n tends to 0. So finally we have this, the whole term tends to 0 as m tends to infinity. So we can neglect this term by taking limit m tends to infinity. Now here we take limit m tends to infinity here, then you can get this m minus 1 tends to infinity, then this becomes, the left side becomes, this implies, I'll write by taking limit m tends to infinity, summation n equal to 0 to m cn x raised to n equal to, by taking limit m tends to infinity here, so that will be this will be 1 minus x times summation n equal to 0 to infinity, because m tends to infinity implies m minus 1 tends to infinity. So this will be Sn x raised to n. So the right side will be like this, the second term tends to 0, so the right side will be summation n1 minus x times summation n equal to 0 to infinity Sn x raised to n. So what is the left side? Left side will be limit m tends to infinity, this quantity. Okay, so that is nothing but our f of x. Okay, so that is 0 to infinity cn x raised to n. So that will be our f of x, that is equal to 1 minus x summation n equal to 0 to infinity Sn x raised to n. So this is the power series expansion, or another representation for f of x in terms of Sn rather than Cn. Okay, we have discussed or we have put this f of x in terms of Cn first, then now we can get a new representation of this f of x in terms of sequence of partial sum of that sigma Cn. Okay, because we need to prove that limit x tends to infinity, x tends to 1, f of x equal to summation Cn. Okay, summation Cn is denoted by some s. Suppose this is n equal to 0 to infinity, we denote that some whole sum as s, which is the limit n tends to infinity Sn. So that since Sn is the sequence of partial sum of this series, so we need to prove this limit is nothing but this s, or limit n tends to infinity Sn. Okay, so this is the requirement. So that's why we need to get a expression of f of x in terms of the sequence of partial sum of sigma Cn. Okay, so that is the idea here. Now as this Sn converges to s for every epsilon, as this Sn converges to s, then for every epsilon greater than 0, we can choose n such that n is the natural number such that, so that for all n greater than or equal to n or greater than n implies we have mod s minus Sn is less than epsilon by 2. After this n, you can get this modulus is always less than epsilon by 2 because Sn converges to s. Okay, now we know that we have the summation, we know that this 1 by 1 minus x will be 1 plus x square plus etc., or the other way you can write it as summation n equal to 0 to infinity x raised to n. Okay, so since this mod x is less than 1, this can be considered as an infinite GP. Then sum of the terms of infinite GP is nothing but 1 by 1 minus x, a by 1 minus the common ratio. So this implies 1 minus x summation n equal to 0 to infinity x raised to n will be 1. Okay, by multiplying it with s on both sides, then this will be s times this is equal to this time s. Okay, then you can take this s inside this summation, because the summation depends upon this n. So we write 1 minus x summation n equal to 0 to infinity s times x raised to n equal to s. So we can get a new expression for this s. Okay, now we consider the modulus f of x minus f of x minus s. Okay, because we will make this modulus less than epsilon as x tends to 1. That is the idea here. Okay, so we need to we need to prove this this limit x tends to 1 f of x equal to s. In order to prove this, we will prove for every epsilon greater than 0, mod f of x minus s is less than epsilon as x tends to 1. Okay, so that is the meaning of this. So we observe this to make this modulus less than epsilon. We use the expression of f of x defined here. Okay, so that is 1 minus x times summation n equal to 0 to infinity Sn x raised to n, and we use the expression of s from this equation. So we write it as minus times 1 minus x summation again n equal to 0 to infinity s times x raised to n. Okay, this is the expression for s and this expression for f of x. Both can be replaced. Then this will be by taking or combining these two. We can write 1 minus x can be taken out, and this will be summation n equal to 0 to infinity. This is Sn minus s x raised to n. Okay, so this is the combining of these two summation. So we can write it as this is less than or equal to by taking triangle inequality. 1 minus x is always non-negative because x is always less than or equal less than 1, so that can be written as 1 minus x as itself, and summation you can take this 1 minus x inside also, and we write this as n equal to 0 to infinity modulus of Sn minus s into x raised to n mod x raised to n. Okay, so this is the idea here. Now we write this summation equal to 0 to infinity as summation n equal to 0 to capital n and summation small n is equal to capital n plus 1 to infinity. So we write that as 1 minus x summation n equal to 0 to n mod Sn minus s mod x raised to n plus summation n equal to n plus 1 capital n plus 1 to infinity mod, here we have 1 minus x as well, so we write 1 minus x times 1 minus x times summation n equal to n plus 1 to infinity mod Sn minus s into mod x raised to n. But we know that this value is always less than epsilon by 2. We have already right here s minus Sn is always less than epsilon by 2, so we can make this is less than epsilon by 2. When we use this, then we can write it as less than 1 minus x summation n equal to 0 to capital N. It is always finite number of terms, contains only finite number of terms, Sn minus s mod x raised to n plus 1 minus x times when you replace this quantity by epsilon by 2, we can get n is equal to n plus 1 to infinity mod x raised to n times epsilon by 2. Okay, but we know that this this quantity is always when we consider this, we can say that this quantity is less than epsilon by 2, because this can be written as this is equal to 1 minus x summation n equal to 0 to n mod Sn minus s mod x raised to n plus this can be replaced by 1 minus x times summation n equal to 1 to infinity mod x raised to n. Okay, because this is always always positive quantities, so we add n capital N number of non-negative terms to this sum, then this sum increases, so this is always less than or equal to this one times epsilon by 2. But we know that this quantity is 1, so we write that is equal to 1 minus x summation n equal to 0 to capital N mod Sn minus s mod x raised to n plus epsilon by 2. Okay, now this left side is f of x minus s. This modulus is always now we write modulus is always less than epsilon, this term plus epsilon by 2. Okay, now we take x approaches to 1. Okay, or choose delta. This is our 1 and this is minus 1. Here we have x. Okay, so choose delta such that that means as x tends to 1, this quantity tends to 0. Okay, and as x tends to 1, this whole quantity tends to n equal to 0 to capital N mod Sn minus s, which is a finite number. Okay, I will call it as some capital M. Okay, since this as x tends to 1, this 1 minus x tends to 0, for every epsilon we can choose this delta such that this whole quantity is less than epsilon by 2. Okay, because the whole quantity tends to 0, that is 0 into m, that is 0. Okay, so we can for any epsilon greater than 0 we can choose delta such that delta less than x less than 1, we have the whole quantity. This whole quantity tends to 0 because that whole quantity, modulus of that whole quantity less than epsilon by 2. Okay, so choose delta such that this whole quantity is less than, choose delta in such a way that delta less than x less than 1, choose delta such that we write this as choose delta such that this quantity, that is 1 minus x summation n equal to 0 to n mod Sn minus s into mod x raised to n less than epsilon by 2, as whenever we have delta less than x less than 1. Okay, so this is possible because this whole quantity tends to 0 as x tends to 1. Now we have for the same delta mod f of x minus s less than epsilon by 2 plus epsilon by 2 whenever delta less than x less than 1. Okay, so this is nothing but epsilon. So this implies limit x tends to 1. Okay, this is only a one-side limit because f of x defined only on the interval minus 1 to 1. So there is no f of x is not defined at these points, so we can never expect the limit from the right hand side of 1. So limit x tends to 1 means the left hand limit of 1. So limit x tends to 1, f of x is equal to s, which is equal to summation n equal to 0 to infinity cn. Okay, so this proves the theorem. Okay.